Hi, my name is Dan Fris, and I'll be presenting the full paper that we presented at SIGIR 2026, Diagnosing Identifiability in Two-Tower Models for Unbiased Learning to Rank, which is a work that I did with Philip Hager at the University of Amsterdam. And the purpose of this video is, well, to reiterate the presentation I gave there, so it's open for everyone to see and to encourage your interest in our work. So our work is positioned in the field of unbiased learning to rank, where we aim to learn from user interactions. And importantly, user interactions are biased by the way we present our results. And there are many ways in which we can present our results and get our data from it, but the classical example is selection bias or position bias in web search. So for example, we present items in a certain way, in a certain order, and top-ranked items are more likely to be observed and subsequently clicked. As a result, the clicks that we gather are biased relevance signals, and unbiased learning to rank considers how we can learn ranking models from these biased clicks. Now, a popular approach in industry settings has become the use of two-tower models, which learn the probability of a click from a combination of two neural networks, also referred to as towers. One of which is the bias tower, which takes into account features that could influence the bias, such as the position. And the other one is the relevance tower, which takes into account relevance features, such as query document similarity scores in a BM25 score or an embedding. We jointly optimize these neural networks on the click prediction task. So what is the probability of a click? And we can then, after we have optimized this, we can use the relevance tower for the relevance prediction in ranking tasks. So this generally works well. However, a topic that has recently come up in some research is the topic of identifiability. Is there a single combination of bias and relevance parameters which explains the observed clicks? So to illustrate this, we have an example. So we consider a set of clicks at 4 positions, click probabilities, with a lighter shade indicating a lower click probability. We then consider an example for how these clicks might be explained from a combination of bias and relevance. So on the left side, we see the bias, and it's a shaded area that gets lighter as it goes down. So position bias decreases with a lower position, and the relevance remains constant for these 4 documents. However, we could also consider an alternative decomposition. For example, we might say the relevance decreases with the position and the bias remains constant. And for using two-tower models in practice, it's very important that we only have a single decomposition, because if multiple combinations are possible, it's not really realistic or useful to use our relevance tower for the relevance prediction tasks, because if we can freely switch this bias and relevance score, our relevance score is quite meaningless. So recent research has asked, when is our model actually identifiable? And it's identified 2 conditions. So first, if we have ranking swaps across positions, we are identified. And what this means is that if we observe a document at 2 different positions, the relevance of the document naturally stays the same. So the change in click probability must be explained by the difference in position bias. So this allows us to know the position bias. And the second condition is if we have a sufficient amount of overlap in our features. And what this can mean is that documents with similar features may have similar relevances, and then we can again derive this difference in position bias from the difference in click probability. However, these existing guarantees are only theoretical, and questions that we are currently faced with is how many ranking swaps are actually sufficient for a model, and how much feature overlap do we really need for our model. And actually, what we are faced with and what practitioners really need is a measure for knowing whether a model dataset combination is identifiable. And this is also what we ask in our work, and we propose a method to do so. So I'll first go over a bit of an intuition for this work, and then we'll go into our method. So we propose using the profile likelihood for diagnosing identifiability. And the profile likelihood is a method that's commonly used in bioinformatics for identifiability analysis, but we adapt it for learning to rank. So we consider here in this graph two data sets, one which is deterministic and one which is random in the way that rankings are displayed. And for both data sets, we have no overlap in the features whatsoever. So this means that when we display all items in the same ranking every time, we are not identified, and as a result, we can freely shift the parameters. And for the random setting, we are identified because we can observe one document at multiple positions, and hence we can derive the difference in position bias. And so what the profile likelihood, what the idea is that we shift and freeze the value of a bias parameter, and we measure the difference in the loss. So what we can see here for the deterministic setting is that when we shift the value of the bias parameter, and we retrain the model and measure the loss, that the loss remains completely flat. So this means that with a different value for our bias parameter, we can still get the same loss, and hence multiple parameter combinations are possible. When we have the random setting and we are identified, we observe that when we shift this value of the bias parameter, the loss decreases. So we are not able to recover the same loss. And this indicates to us that we only have a single set of optimal parameters, and hence we are identifiable. And so we apply this as a method for diagnosing identifiability. So what we do is quite straightforward. We shift a value of a bias parameter away from its optimum, we freeze it, and then we retrain the rest of the model. We then compare the loss of the shifted model with the loss of the original parameters and evaluate if the loss difference is statistically significant with the likelihood test. And importantly, we shift in two different directions, so we can shift a value up and a value down. And if the threshold is never exceeded, we have structural unidentifiability. What this means is that our parameters do not constrain our model enough whatsoever, and we need to change the way in which we gather data to be identified. If the threshold is exceeded on one side, so shifting either up or down, then we have practical unidentifiability. What this means is that when we gather enough data, so if we gather more data, we can constrain the parameters further and we can reach identifiability. If we find that the threshold is exceeded on both sides, we have found identifiability. And importantly, we use a statistical test, which allows us to have a statistical significance result using this likelihood test. We can repeat this for all bias parameters to determine the identifiability of our whole model. So we use two experiments in this setting to both demonstrate how our method works and to validate our findings, validate our ideas. So first we investigate how parameters of the data sets such as feature overlap, swaps in rankings, and sample size affect identifiability. And we consider whether we can diagnose identifiability issues in real-world datasets. So first we consider the effect of dataset parameters on identifiability. And these are a bit complex graphs, but I'll walk you through them. So first let's look at the left side where we simulate a fully synthetic dataset. We simulate, in this setting, no feature overlap across different ranks. So what is shown is the shaded areas indicates the feature values which are generated for each rank at which a document can be displayed for 10 ranks. And we sample a random relevance logit or relevance score for each feature values across a randomly generated curve. And what this means is that we have no overlap in our features across different ranks. And we then test identifiability for this. So this is the left graph on the right side. And what we see here is when we shift, so this is the x-axis, we can test the likelihood difference. So we can see whether it exceeds the different statistical thresholds which we have set. And we can do this for different numbers of queries. And what we see in this graph is that no matter how many queries we simulate, we do not exceed the threshold. There is some noise, but the likelihood threshold is not exceeded. When we introduce randomness, so if we introduce swaps in these rankings, we are theoretically again identified, and we can see this in that when we simulate enough queries, then we are exceeding the threshold and we are identified. So we can also consider a setting with feature overlap. We can see this when we look at the simulated feature values on the left side again. We can see that the shaded areas now have some level of overlap. And when we have this overlap, we can derive somewhat the identifiability. If we have enough data, we can constrain the parameters. So we can see again on the left graph on the right side, when we simulate enough data, when we simulate 500 queries, we can exceed the thresholds and we reach identifiability. On the right side, so all the way on the right, we again consider a setting with randomness. And there we can see we can still exceed the identifiability thresholds and we can do it even faster. So 100 queries is already sufficient. So we have now shown that given enough data and constraining specific data settings, we can diagnose identifiability and that this aligns with the theory. And we now consider whether we can actually diagnose identifiability in a real-world data set, which is what practitioners will be used to. So we consider one of the largest real-world click data sets that is currently available, which is the Baidu Unbiased Learning to Rank data set. And here we train a two-tower model with 20 positions, so 20 position bias parameters, and we perform identifiability testing for these parameters. And we color these results for the identifiability analysis with the different results that we found. And we show the results for each parameter index. And what we find here is that actually several low rank parameters, so towards the lower side, are structurally unidentified. So we find no identifiability at all. And even some higher ranked parameters are practically unidentified, so need to have more data to be identified. And the important takeaway from this is that identifiability issues persist even in large click data sets. So it's important to apply this testing and important that our work can help in diagnosing these real-world issues and potentially help practitioners or researchers find solutions to identifiability. So this is our work. The takeaways from our work are that we provide a diagnostic method for identifiability of two-tower models for a given data set. Identifiability strongly depends on feature overlap, logging policy randomness, and the number of samples. And finally, identifiability issues persist in real-world data, even when sample sizes are large. So this is our work. If you have any questions about it, feel free to send me an email or leave a comment, and I'll be happy to answer them. Thanks.